The opening ceremony will take place from now until 5 p.m. We will be hearing addresses from distinguished members of the organizations that have made this event possible, as well as a plenary speech by our honorary guest, Dr. Ryoji Noyori, University Professor at Nagoya University, President of RIKEN, and Nobel Laureate in Chemistry. First on our program is a welcome address by Professor Dr. Pirom Kamonratanakun, President of Chulalongkorn University. Please welcome Dr. Pirom to the stage.
Special events that coincide with this academic gathering is the centenary of the establishment of the Faculty of Engineering at Chulalongkorn University on June the 1st. As you all know, the main theme of this 5-day academic event is Green Science and Technology for a Sustainable Future. And the lectures and presentations are grouped into two substreams: green mobility and energy, and agricultural science and food production, which are the major concerns in our urbanized society. We have all become aware that our easier and more comfortable life have been achieved at the expense of our natural environment. This venue is where 80 graduate students from members of the AC21, as well as non-members from Thailand and its neighboring countries, are to meet and work together in order to achieve the objective of this forum. Here, they will learn from a series of lectures by Thai and international scholars, as well as experts in green science and technology. We hope that this lecture will inspire and motivate the young participants to develop the group's projects that they will be presenting at the concluding session at the event. This academic meeting has been organized to provide the opportunity for academics and interested parties to come together to discuss and discover ways of coping with and therefore reduce environmental problems. It is our earnest hope that the result of our discussion will be put into practice and be used as a way of motivating our society to keep our future world green and ensure an adequate supply of agricultural products to sustain our population. I would like to bring your attention to the fact that to celebrate its milestone, the Faculty of Engineering, in cooperation with Nagoya University, has invited Professor Dr. Ryoji Noyori, the Japanese Nobel Laureate in Chemistry, to give a plenary address entitled "Science Shapes Your Future" in this afternoon. His speech will certainly inspire the participants at this event to improve their teaching and research activities. Again, on behalf of the administrators of the whole university and the organizing committee, I would like to welcome you to this AC21 International Graduate Summer School. I hope you will enjoy your stay in Bangkok and will be successful in all your activities over the next 4 days of discussion. Thank you very much.
Thank you, Dr. Pirom, for introducing us to the goals of this event and welcoming us today. Now, it's time for a welcome address from our co-host, Ksait Saad University. Please welcome Associate Professor Siri Chaiseri, Vice President of Ksait Saad University, to the stage.
Dr. Michinori Hamaguchi, President of Nagoya University, Professor Pirom Kamon Ratanakun, President of Chulalongkorn University, Professor Dr. Ryoji Noyori, honorable speakers, distinguished guests, ladies and gentlemen. May I first convey the message from the President of Kasetsart University that he feels unpleasant not to be able to join this very special event owing to the prior commitment. On behalf of Kasetsart University, it is my great pleasure to extend a very warm welcome to all of you. Kasetsart University is very privileged to co-host the AC21 International Graduate Summer School today. Nagoya University, Chulalongkorn University, and Kasetsart University have had a long history of academic collaboration through the Academic Consortium 21 platform. Several activities have been conducted. Among of them includes a forum that gives students from AC21 member institutions the opportunity to discuss international issues. This year, the AC21 International Graduate Summer School is jointly hosted by Kasetsart University, Chulalongkorn University, and Nagoya University. Its major objective is to enhance the academic strengths, particularly of graduate students from AC21 members and those from non-AC21 member institutions in the neighboring countries of Thailand. The main theme of this forum focuses on green science and technology. That is the most essential trend in the 21st century. All mankind learn to get back to living in harmony with nature while they keep up with the advancement of science and technology innovations. This new paradigm will definitely bring forth our sustainable global society. Moreover, this special forum values the friendship among all participating graduates. They will be better connected with our activities designed to motivate them, not only to share their knowledge of science and technologies, but to form personal linkages with one another. Ladies and gentlemen, may I wish you all very success with this event and a memorable time in this beautiful city of Bangkok. Once again, welcome to AC21 International Graduate Summer School, and we are also awaiting to welcome you all to our Green Campus during the 1st to the 4th of June. Thank you.
Thank you, Dr. Siri, for your warm welcome on behalf of Kasetsart University. Next is a welcome address from our other co-host from Nagoya University. Please welcome Dr. Michinari Hamaguchi, President of Nagoya University and General Secretariat of AC21 to the stage.
Ladies and gentlemen, distinguished guests, on behalf of Nagoya University and as one of the co-host university of the AC21 International Graduate Summer School, AC21 IGSS in short, I would like to offer our warmest welcome to our distinguished guests, sponsoring organizations and companies, keynote speakers, lecturers, and of course students and delegates of the AC21 member universities. AC21 celebrated its 10th anniversary in June last year. We are very grateful for the support and the cooperation provided to AC21 by the member universities, governmental institutions, and companies, which has helped AC21 to expand its activities such as the SE21 IGSS here today we have, and enabled Nagoya University to manage the General Secretariat of this international scale consortium. Looking back on the past 10 years, the environment surrounding us has changed drastically. Since both the positive and negative impacts of globalization were brought to public notice, public awareness of global issues such as shortage of food and energy has been growing. These global issues cannot be solved without international collaboration. That is why the international academic consortia like AC21 are designed to promote it. The main theme of AC21's new project, AC21 IGSS, is green science and technology for a sustainable future. The AC21 IGSS addresses two sub-themes dealing with current global issues. One is green mobility and energy. Another is agricultural science and food production. I hope the AC21 IGSS will help promote further understanding of these global issues and also enhance intellectual exchange among the scholars, students, practitioners, and policymakers attending this symposium. In conclusion, 3 years ago, President Pirom Kamsatanu visited our university and requested to plan the school, summer school for new type motor automobiles. I would say our dream we planned 3 years ago now comes true today here in Bangkok. We really appreciate the Coast University, Chulalongkorn University, and Kasset South University for their dedicated work toward making this event to be successful. And of course, congratulations for the Faculty of Engineering of Chulalongkorn University for the 100th anniversary. We are very happy to celebrate together with you today. And one more point I would like to tell you, my fellow students. Our future is in your hand. So try your best and believe your future. This is what I want to tell you today. Now, we will make first step to open a new future. And I hope everybody attending this symposium have fruitful weeks here in Bangkok. Thank you very much for your attention.
Thank you, Dr. Hamaguchi, for your words of welcome on behalf of Nagoya University and for shedding light on the importance of international cooperation in our future. Now, it's time for a greeting address by Mr. Etienne Clement, Deputy Director of UNESCO Bangkok. Please welcome Mr. Clement to the stage.
Professor Pirom Kamal Ratanakul, President of Chulalongkorn University, Professor Dr. Michinari Yamaguchi, President of Nagoya University, Associate Professor Siri Chaiseri, Vice President of Kasetsart University, Associate Professor Bunsom Lerdirungwang, Dean of the Faculty of Engineering. Ladies and gentlemen, it's an enormous pleasure for UNESCO to have been invited today for this very important International Graduate Summer School celebrations. I'm particularly pleased on behalf of UNESCO to greet all the participants from near and far to the Academic Consortium for the 21st Century International Graduate Summer School. I would like also to take this opportunity to extend my best wishes for the Faculty of Engineering of Chulalongkorn University, which is celebrating today its 100th anniversary. Congratulations. Charles Darwin once pointed out that in the long history of humankind, and presumably animal kind too, those who learned to collaborate and improvise most effectively have prevailed. It is with this statement in mind, it is great to see that so many people and representatives for various institutions and various backgrounds and disciplines are here today. And indeed, collaboration does not only foster peaceful, trustful, and positive relations between nations and people, but it also helps us expand our horizon and refresh our ideas, leading to innovation and progress. So the theme of this year's summer school, Green Science and Technology for a Sustainable Future, is of utmost importance in our work towards achieving sustainable development. In order to feed the world's growing population in an era of dwindling natural resources, we need to develop and promote more sustainable methods of food production that help sustain our planet's ecosystem. We must also develop and promote more energy-efficient infrastructure and methods of transportation and production that are in line with the values of a green economy. Education is an indispensable element in meeting these challenges. It is through education that we can build the capacity of our future researchers and scientists, and it is also through education that we can achieve changes in behavior and lifestyles. As the lead agency for the United Nations Decade of Education for Sustainable Development, 2005-2014, UNESCO, which I have the honor to represent today, works to expand access to education for all and to equip and empower learners with the skills, attitudes, and values necessary to achieve sustainable development. A concrete example of our work is the 600 biosphere reserves UNESCO has designated as learning sites for sustainable development. Many of these cultivate organically produced food and textile which help to conserve biological diversity and promote rural employment. In our work to promote greater sustainability, it is crucial to remember that as a complex and multifaceted, our challenges as encompassing and multifaceted must our solution be. This means that we must adopt not only an international response, but also an interdisciplinary response. It is by enabling collaborations and drawing on each other's pool of knowledge that we can plant the seed for future success and let innovation blossom. Therefore, I'd like to invite you, and I'm also then addressing to the students, to commence and go through this week with an open mind and heart, to listen carefully, to learn, to ask questions and share your ideas. Because it is when we work together and listen to each other that we will reach further. So all the students Please prepare yourself to be challenged, excited, intrigued, and inspired. And importantly, remember that change must start with each of us, with the way we think and act. We all hold the future of our planet in our hands, and together we can all make a difference. Thank you very much.
Thank you, Mr. Clement, for stressing to us the importance of education in creating a more sustainable and peaceful future in your inspirational address. Next is a greeting address by Associate Professor Dr. Bunsom Lerthiranwong, Dean of the Faculty of Engineering, Chulalongkorn University. Please welcome the Dean to the stage.
Professor Vishanali Hamaguchi, President of Nagoya University. Professor Philom Komon Ratanakun, President of Chulalongkorn University. Associate Professor Dr. Siri Chai Seri, Vice President of Kasetsart University. Nobel laureate Professor Liu Ji, now Yuri. Mr. Etienne Cremont, Deputy Director of UNESCO, Bangkok. Mr. Takeshi Yuichi Yamada, Vice Chairman of the Board, Toyota Motor Corporation. Distinguished guests, ladies and gentlemen, and beloved students, on behalf of Faculty of Engineering, Chulalongkorn University, may I take this opportunity to express the faculty's great appreciation to Nagoya University, Kasetsart University, and Chulalongkorn University for agreeing to co-host the AC21 International Graduate Summer School Program to coincide with the 100th anniversary celebration of the establishment of the Faculty of Engineering. To mark this important milestone, Juฬา Engineering, with high cooperation from Nagoya University, has the honor of presenting to you Professor Dr. Ryuji Noyori, Nobel laureate in chemistry from Nagoya University, who will shortly give a plenary speech entitled Science Shapes Your Future. We have asked Professor Ryuji Noyori to speak to us this afternoon on this important topic because we, as an engineering education institute, take seriously our role in educating future engineers who once graduate will carry an important charge with them, that is, to shape and create the future for all of us. But before we can reach that goal, we take this moment to remind everyone that a bright and sustainable future is possible only with a solid foundation. Much like science is the foundation on which engineering can flourish. For a century now, Juฬา Engineering has proven itself as an institute that provides a solid foundation from which the Thai's economy and society has reaped the benefits. We are proud of our successes and our past, but we cannot stop here. The future is where all of us are heading. The solid foundation of the past can only ensure that we are well prepared for the unknowns of the future. But is there a better way to prepare for the unknowns of the future than to shape and create the future by ourselves? The future is in our hand, ladies and gentlemen. That is why July Engineering regards the 100th anniversary of our establishment not only as an important milestone for celebration of our past, but also as a crucial turning point where we transform the Faculty of Engineering, arguably the best engineering teaching institute in Thailand. For the past 100 years to July Engineering of the Future, where innovations from research and collaborations with both domestic and international partners lead the ways of engineering, research, and education for the decades to come. Ladies and gentlemen, foundation toward innovations, that is the chart we put in front of us, a vision for the future of our institute, which will in turn shape and mold the future of Thailand and the region. As we integrate more closely into regional and global economies and society, I take this opportunity to thank our friends and partners who have made significant contributions to our successes, without whom we certainly would not have made it this far. I thank you dearly, and I hope that we can count on your friendship and support for the years to come. I once again thank you all who are present in this auditorium with me for joining our celebration of the success of our first 100 years and for standing as a witness of the crucial transformation that we pledge to you here today. Better days are ahead of us. Let us join hands and shape our future together. Thank you.
Thank you, Dr. Bunsom, for informing us of the increasingly important role of engineering in shaping a better future. Now, for the highlight of the afternoon, we will be hearing a plenary speech by our honorary guest, Professor Dr. Ryoji Noyori, entitled Science Shapes Your Future. But first, let me say a few words about our very distinguished speaker. Dr. Noyori is the president of RIKEN and university professor of Nagoya University. He is also a member of the Pontifical Academy of Sciences and the Japan Academy, foreign member of the National Academy of Sciences USA, the Russian Academy of Sciences, the Royal Society UK, and the Chinese Academy of Sciences. Born in 1938, Dr. Noyori was educated at Kyoto University. After serving as an instructor at Kyoto University and associate professor at Nagoya University, he went to Harvard University as a postdoctoral associate. He was appointed professor at Nagoya University in 1972 and assumed his current positions in 2003. He received the Japan Academy Prize in 1995, the Order of Culture in 2000, and the Wolf Prize in 2001. That very same year, he was also awarded the Nobel Prize in Chemistry with K. Barry Sharpless and William S. Knowles. Now, Dr. Noyori will share with us his valuable insights on the role of science in our society. Please welcome Dr. Noyori to the stage.
Thank you. Thank you very much. You are very accurate personal introduction. No mistake at all. So, good afternoon, distinguished guests, ladies and gentlemen. It's my great pleasure and honored to be here at the most prestigious Chulalongkorn University for the joint opening ceremony to celebrate the centennial anniversary of the Faculty of Engineering and also the AC21 International Graduate Summer School, which is held with the unfailing efforts and hospitality of Chulalongkorn University and also Kasetsart University. I'm very pleased to give an opportunity to have an opening lecture to the talented students and the young researchers, largely from Asia, particularly rapidly developing Thailand. Science is continuously generating new knowledge about nature. It's an intellectual endeavor that has been joyful and exciting. Notably, however, the relationship today between science and the society is very much different than it was in the time of Galileo, Newton, or even Einstein. Science, particularly our science, chemistry, is closely intertwined with society. I perceive the value of science in the following way. Basic science is the fountainhead of human knowledge and has eternal cultural value. The technology that we gain from scientific knowledge is the foundation of civilized society. And creative innovation derived from science and technology is what makes us internationally competitive and assures our continued survival as independent nations. Furthermore, innovation is also an essential aspect of our international contribution to assuring the continued survival of humanity. This is why we were involved in scientific research. In fact, I'm a chemist. Simply stated, chemistry is a science of substances and materials. We try to understand substances and materials involved in all natural phenomena on atomic and molecular levels. We also try to create and manufacture new compounds with desired properties and functions at will. Well, chemistry is therefore very important. So this means that we can generate any functions or properties by using the accumulated chemical knowledge. In this regard, the green chemistry here is becoming extremely important now. It is creative, prosperity-bringing, and also responsible science. The essential aspect of green chemistry is as follows. We have to use safe starting materials and renewable resources, and also the safe solvent. We should avoid to produce toxic waste. We should conserve energy and green energy, and also we should avoid the toxic waste. Well, in fact, the green chemistry has just begun, and it will not easy to achieve the object as you see here. Today, I'll be talking some example of green chemistry achieved in my laboratories at Nagoya. First, green chemistry needs non-toxic, safe solvent. So in this regard, we initiate a catalysis in supercritical CO2 for the first time some 20 years ago. This compound, CO2, has a triple point here at 31 degree and at 73 atmospheric pressure. When CO2 is heated above this temperature, 31 degrees, it cannot liquefy, even if we apply a high pressure, instead forming a supercritical CO2 phase. Interestingly, the physical properties vary drastically near the critical point and the influence of under the influence of pressure and also the temperature. The density, for example, changed by a factor of 10 to the third, meaning that the average molecular distance could change by a factor of 10. In addition, solvation power of CO2 is weak, and therefore some unique molecular clustering might occur locally in supercritical CO2. Furthermore, CO2 has a range of technical benefits. It's non-toxic, non-flammable, and also very cheap. It can be easily separated from reaction system without leaving any harmful residue. Thus, overall, supercritical CO2 is very, very attractive reaction medium from both a scientific and also a technical point of view. We found that a ruthenium catalyzed reaction, hydrogenation of CO2, proceed with a very high productivity and under supercritical conditions, giving formic acid, methylformate, and DMF with the aid of triethylamine, methanol, or dimethylamine, depending on the target molecules. This experiment clearly indicates that supercritical CO2 is very, very attractive reaction medium. I strongly recommend you to use supercritical CO2 for certain chemical reactions or catalysis. So needless to say, the chemical synthesis occupies a central place of our science. Chemical synthesis frequently utilize fossil resources or petroleum or coal or biomass or also the inorganic compounds such as H2O2, halogen, water, ammonia, CO, and the CO2. Then in order to combine these compounds and transform them to useful compounds, we need efficient catalysts, reagents, or enzymes. Here, the development of efficient catalysis is crucially important since nowadays more than 80% of the commercial products are produced by catalysis. The state of the art of chemical synthesis is amazing. Our experts can synthesize such important compounds such as chiral anti-cancer agent, chiral AIDS agent, anti-ulcer agent, or antibacterial. Without these man-made compounds, we are unable to survive healthy. So develop, particularly atorvastatin or Riptol, developed at the Pfizer company on the basis of Dr. Ando's original discovery, efficiently reduces cholesterol levels. Some years ago, its annual sales exceeded even $15 billion US, although the figure went down markedly now because of their patent expiration. In any case, currently more than 30 million people are treated with these statin drugs, including this Lipitor. The structures of these very important compounds are completely different from simple, very cheap statin materials, which is shown in the previous picture. Thus, the development of new drugs is a sort of a modern alchemy. However, we still have a serious problem in such a chemical synthesis. Roger Sheldon was the first to propose the importance of E factors or eco factors to obtain 1 kilogram of the gasoline by cracking naphtha. We only produce only 0.0 kilogram of waste is a product. But many important organic compounds are produced from raw materials in a multi-step process that gives rise to accumulated waste with the large E factors. For instance, production of 1 kilogram of commodity chemicals resulting in 1 to 5 kilograms of waste, and the synthesis of a specialty chemical produces 5 to 50 kilograms of waste, while the synthesis of pharmaceutical drugs produce 25 to even 100 kilograms of the unwanted waste. Where are the waste going? Of course, the extent of the undesired environmental impact is highly dependent on the properties of the waste. In addition, we must carefully evaluate the balance of the benefits and the waste. We should avoid the hazard-based assessment because the risk is different from hazard. Still, however, reducing the amount of undesired waste is crucial in the chemical industry. And we synthetic chemists have an immense responsibility in this in this respect. Thus, the green chemistry is a key issue for the chemical manufacture in this century. First, let's take oxidation as an example. H2O2, hydrogen peroxide, is a very attractive oxidant for green chemistry, only if you have an excellent catalytic system. This is viewed as an adduct of atomic oxygen and water molecules, and is currently being produced from hydrogen and oxygen, H2 and O2, in a quantity of over 2.5 million tons per year. Now consider the synthesis of nylon 6,6. Nylon 6,6 is an indispensable material for our daily life. In this room, nylon fiber is used in a large amount. In fact, the synthetic fiber is everywhere in our life, in a modern society. And we are unable to live without nylon or nylon 6,6. Nylon 6,6 is a polyamide produced by a condensation of hexamethyldiamine and C6 dicarboxylic acid called adipic acid. Currently, very important, adipic acid is synthesized industrially in this process through AKO, which is produced by a hydrogenation of benzene followed by a low conversion aerobic oxidation to make the mixture of that. This is fine, but the problem is the next step. We are using a nitric acid to oxidize these compounds to give adipic acid. So this is efficient, but the problem is the production of N2O as an unavoidable co-product. Well, the NO2, which we are producing a large amount, has a very, very negative, environmentally negative effect that catalyzes the ozone destruction Also, the N2O has a very, very large greenhouse gas effect. Also, this causes acid rain and smoke. Therefore, you have to recover the N2O byproduct. Unfortunately, concentration of N2O in air is ever increasing. So therefore, we took a note of cyclohexene as a starting material, which is produced by a selective hydrogenation of the benzene to give this one, which it was achieved by Asahi Kasei company in Japan. We found a simple green route to oxidize cyclohexene to azipic acid by using aqueous hydrogen peroxide, which is among the ideal oxidant. This is actually a perfect reaction using 4 equivalent of hydrogen peroxide. We can obtain just a colorless, pure crystalline adipic acid just by simple filtration. So this is just a mechanistic pathway. So this double bond is oxidized by hydrogen peroxide with the aid of a tungsten catalyst. And this is hydrolyzed to give this diol. And this alcohol is dehydrated by hydrogen peroxide to give a hydroxy ketone, which undergoes the Baeyer-Villiger type oxidation to give this compound. Again, this hydroxyl group is hydrogenated to give acid anhydride, which is hydrolyzed to give such a beautiful adipic acid, crystalline form. You now obtain only adipic acid without any waste other than water molecules. This is a very, very ideal green oxidation. The next topic is reduction instead of oxidation, the reverse of oxidation. As many of you chemical students know that over a half century, selective reduction of ketones have heavily relied on the chemistry of metal hydride or organoboranes developed by Herbert Brown, who was a Nobel laureate in 1979. Such organoboron-based methods are convenient but produces a large amount of metal or boron-containing waste. And obviously, they do not meet with the demand of this century's environment-friendly chemistry. Then we have long been engaged in the replacement of this boron-based reduction process by a clean catalytic hydrogenation using a molecular catalyst. So hydrogen is the smallest and the simplest molecule, and the hydrogen gas is a very clean resource, ideal for green chemistry, as long as we have an efficient catalyst. So no waste is formed by hydrogenation at all. The E factor is 0 in principle. And this, my dream, came true. A very simple ruthenium, phosphine, and diamine complex catalyze the hydrogenation of such compound, ketone having olefinic substances, to give this type of compound. So this double bond is not hydrogenated, while this ketone is converted to alcohol. So the presence of NH ligand on the ruthenium is crucially important to exert this catalytic hydrogenation. So this provided a very important breakthrough in organic synthesis. So you no longer need sodium borohydride reduction for this kind of reduction. Also, you can hydrogenate this kind of ketone to give this stereochemistry. The more important is this asymmetric version of hydrogenation of ketone to give such a chiral compound. So this is the most important subject which brought me to Stockholm in 2001. And therefore, I will tell you a little bit on this chemistry. Molecules, organic molecules, have three-dimensional structures. And many organic compounds have right-handed and left-handed structures, which are known as enantiomers. The right and left components diverge from each other only very slightly, but we know that this difference can become very large in biological or living phenomena. We know that the enantiomer causes things to taste and smell quite differently. Monosodium glutamate with the S configuration or left-handed component is umami taste enhancer, but the same compound with the mirror image has a bitter flavor. R-limonene smells like an orange, while its enantiomer is present in a lemon. Add oxygen here, and you end up with the R-carbon, right-hand carbon, which is a component in a spearmint. On the other hand, its mirror image is a component in a caraway seeds. And another example is a Darbon drug, which is a painkiller, while this enantiomer is called Novrad, which is an anti-cough agent. And some drugs are excellent, while some right-handed enantiomer is a good drug, but the other enantiomer could be toxic. So the left-handed molecule and the right-handed molecule, that differentiation is extremely important in terms of the pharmaceutical drugs. Well, earlier I showed that the structure of Lipitor or atorvastatin, which efficiently reduces the cholesterol level. Why does it work so efficiently? So Lipitor atorvastatin is a small molecule which is an enzyme inhibitor. This small molecule, Lipitor, is strongly bound to the big enzymes, HMG-CoA reductase, by making such a complex that efficiently prohibit the biosynthesis of mevalonic acid. Such molecular dynamics can now be studied in detail by computation in addition to experimental structural biology. In order to make such a very precise molecular complex, the structures and electronic properties, characteristics of a large and small molecules must be complementary, both electronically and also three-dimensionally. This drug here should have an appropriate surface potential, which is generated by the suitable three-dimensional structures, as well as the existence of heteroatoms like a nitrogen or oxygen functionality. So here you see the two stereogenic carbon centers having OH groups. So thus, molecular chirality or enantiomeric structure is a key issue in our life. Therefore, we need practical methods for the production of enantiomerically pure organic compound. However, it remained quite difficult until we came into this field. So my whole academic career has been a challenge to Louis Pasteur, who stated in 1851, when he was just 29 years old. He said that this symmetry is only and the distinct boundary between biological and non-biological chemistry. Therefore, symmetrical or physical or chemical force cannot generate molecular dissymmetry, according to Louis Pasteur. So rigorously speaking, this is not true, but it was accepted as truth from a practical point of view until just 30 years ago. In any case, chemical synthesis of chiral compounds is extremely important. So we need a chemical principle to tackle this very important, significant subject. The progress of science is totally unpredictable, I'd say. 47 years ago, in 1966, when I was in Kyoto, we discovered for the first time this asymmetric carbene reaction with a chiral Schiff-based copper catalyst to form such a chiral or enantiomeric cyclopropane products. So we use a molecular catalyst containing transition metals and chiral organic compounds or ligands. This now provides the general principle of asymmetric catalysis, which is now widely used in research and also in industry. However, at the time, no one recognized the significance of this science because this reaction was practically meaningless. First, selectivity was just 55 to 45, not 9 to 10 or 99 to 1. And also, secondly, the three-membered ring forming reaction is a bit peculiar, very strange, and not very much generally useful. So here I would just remind you that this poor result is the start of enormous research field. 2 years later, when I was 29, I moved from Kyoto to Nagoya, where I no longer worked on this interesting but useless science. Then we moved to asymmetric hydrogenation. That is very, very general. So we invented a range of very useful transition metal binary catalysts for this purpose. With normal conventional catalyst, we can hydrogenate these compounds to give a 1-to-1 left-handed right-handed compound in 50-50 ratio. However, with our special complex catalyst containing a BiNAp ligand, we can obtain just a single-handed compound with very high energy-numeric ratio, 99-to-1 or 100-to-0 ratio. So this method is extremely important in connection of synthesis of pharmaceuticals, agrochemicals, flavors, and fragrances. These are some examples of important chiral compounds that we synthesize through our asymmetric hydrogenation. The process we developed has a very general application and has come to be widely used in research and industry throughout the world. So this picture shows only some important industrial application of our method. Carbapenem antibiotics are now best synthesized by using the asymmetric hydrogenation of such beta-keto ester using R-binaprothenium complex to give only RS configurated beta-hydroxy esters. This simple asymmetric hydrogenation of acetol to give R-propanediol is also used for the synthesis of levofloxacin or Cravit, which is a very important antibacterial agent developed at the Daiichi pharmaceutical company in Japan. The annual sale of this simple compound is about $3 billion US, the huge blockbuster. The key to our success was the molecular beauty of our catalyst, which is pliant rather than rigid and has rotational C2 symmetry. The chiral three-dimensional space is well recognized or differentiated by the such type of BiNAp transition metal catalyst, thanks to the presence of 4 phenyl rings attached to these 2 phosphorus atoms. The reaction is occurring in these green sites under the control of this BiNAp ligand. The utility of our BiNAp asymmetric catalysis is not limited to hydrogenation. We can synthesize such a L-menthol using asymmetric double bond shift reaction by the BiNAp rhodium catalyst. Since 1983, the Takasago international company has been producing some 3,000 tons of L-menthol every year. So this practical asymmetric synthesis was achieved through extensive academic and industrial collaboration, which is very important to materialize such a big process. So I was visiting this big facility in 1984, almost 30 years ago. In fact, such a recent progress in asymmetric catalysis has dramatically changed the procedures of chemical synthesis of organic compounds having a high degree of structural precision. Today, asymmetric synthesis is central to research and production in $600 billion US global drug market in pharmaceutical drugs. Now then, what is the major impact of our science on society besides the obvious such economic benefits? In 1992, some 20 years ago, the US Food and Drug Administration, FDA, set guidelines for racemic switches. At the time, more than 85% of synthetic chiral drugs were sold as racemic mixture. However, the new regulations strongly urged the pharmaceutical company to manufacture and commercialize purely single-handed compounds. And this regulatory decision contributed to a major improvement in medicine. At the time, some 20 years ago, no such large-scale asymmetric synthesis existed in the world. I believe that the successful technology developed in Japan was a major contributing factor to the important policy change in the United States and also worldwide. Earlier, I told you that a young Noyori of 47 years ago, then in Kyoto, was excited about the discovery of the first asymmetric Karbin reaction, making cyclopropane. However, the reaction was practically meaningless, useless. Honestly, at the time, I was unable to think of what our original discovery might lead to the years ahead. Honestly, I could not foresee the practical synthetic utility. Then I left this subject, asymmetric chemistry, for a while. However, the essence of this chemistry did not disappear. A junior person who happened to be at the Kyoto University laboratory when we discovered asymmetric cyclopropionation was named Tadatoshi Aratani. Obtaining his PhD degree, Aratani joined Sumitomo Chemical Company, where he improved the asymmetric catalysis process to produce cilastatin, which inhibits enzyme degradation of beta-lactam antibiotics. So this was a commercial success made in 1980s. Around the same time, Aratani also succeeded in a large-scale synthesis of chloranthic acid, which is an insecticide to kill mosquitoes. He succeeded in such a big synthesis. Although the technology had been realized, it was never commercialized because, unfortunately or fortunately, there was an unexpected decrease in mosquitoes in Japan. Aratani was unhappy and discouraged. However, just recently, there was another unexpected development in fighting malaria. The technology Oriset net developed at the Sumitomo Chemical Company, is now being used in the WHO's battle to eradicate malaria in Africa, particularly Tanzania. Every year, 300 to 500 million people in a year are infected with malaria by Anopheles mosquito. Of this number, more than 1 million, most of them children, die of this disease. And around 90% of these deaths take place on the African continent, south of Sahara Desert. The economic loss is estimated at around 15 billion US dollars. Sumitomo chrysanthemate insecticide called permethrin is being used in a high-density polyethylene mosquito net. And Sumitomo Chemical has been providing this technology free of charge. And thanks to this Japanese technology, some 8,000 jobs have been created to help support Tanzania's population of 70,000 people. Well, roughly half a century has passed since our unforgettable discovery of S-metal catalysis in Kyoto. We'd have thought that our discovery so many years ago would eventually lead to such an important contribution to global welfare. I wonder what lessons you will take from this story. What does it teach you about science, technology, and innovation? And what are the necessary factors to bring this all about? This is difficult to answer. Well, I talked some examples of green catalytic chemistry generated in my research group in Japan and its industrial or social impacts. But this was just a modest example that shows the significance of basic sciences. Some years ago, or 10 years ago, the National Academy of Engineering in the US characterized the 20th century as a century of innovation and selected these 20 greatest technologies that have changed our lives decisively during the period. The first was the electrification, and this was followed the Toyota automobile manufacturing, airplane, water supplies, electronics, and so on. So without these innovations, we could not have realized the affluent civilized society we live in today now. In addition, this list shows the contribution of chemistry is enormous. Chemistry is everywhere. Without chemistry, we cannot drive cars or fly aircraft and spacecraft that are made of so many kinds of man-made materials. We cannot drink water without chemicals because water is now supplied through cheap and durable pipes made of polyvinyl chloride. and certain chemicals enhance food production and also cure our illness and much more. And notably, most of the important compounds used today are artificial products created by chemists. Naturally occurring compounds are very important, but not enough to sustain our civilized society. So thus, I'm very proud of being a chemist. And now we need green chemistry, as I described, and otherwise we human being is unable to survive anymore. So, green chemistry should not be a mere catchphrase, but an indispensable principle that will sustain our civilized society in this 21st century. I'd like to emphasize that this concept is not a matter of clear-cut scientific or technological expertise, but rather a serious social issue. In order to materialize our research goal in the real world, we need a rational long-term program supported by the public understanding, governmental policies, and worldwide cooperation. Green chemistry is crucial in our society. In fact, however, there are greater issues that we confront us in this 21st century. That is here. In his summary at the 2002 Earth Summit in Johannesburg, former US Secretary General Kofi Annan stated that the most important issues confronting humanity today are we have plus P, that is water, energy, health, agriculture, biodiversity, and eradication of poverty. They are the highest priority task for humankind. And of course, environmental issues encompass all of these areas. Since science and technology do not exist only to make nations internationally competitive, science and technology are fundamental elements of human beings or human society. We and everyone in younger generation must move forward with this in mind. Louis Pasteur once stated, science has no borders, but scientists have their own fatherlands. That's an important statement. So this is a message, my message to younger researchers and the students everywhere. Well, the places and the people of our early years all have their own cultures. We have to respect this cultural diversity. Scientists and the technologists in this century must create a civilization that respects cultures. The 20th century, last century, was an era of international competition, symbolized by war and economic rivalry. In this 21st century, however, we'll have to cooperate internationally for the survival of our species within the limit of this planet. Countries all have different histories and viewpoints, and their interests sometimes often clash. But no countries, even China or United States, such big country, can exist on its own. Everything begins with understanding between individuals. I'd say friendships across the seas and firm relationships of trust are the cornerstones of international securities. Finally, I would add a statement of Terada Trajiko, who was a leading physicist and well-known writer of essays in Japan. We scientists often complain against the government, politicians, and policymakers who little understand science. However, Terada wrote that it's not the ignorance of the amateur that obstructs science, but the scientist's own lack of mission and characters. And he said that we should think carefully about this. I hope those of you here today who aspire to become scientists will take these words to heart. Science means different things to different individuals, groups, and sectors of a society. For human society as a whole, however, science has a very critical value, and the technology arising out of science is essential not only for industry and economic activity, but for the continued existence of human society. My young cohort, you have within your great potential. I very much hope that you will come to fully understanding in your future activities. Thank you very much for your patience and listening.
Thank you, Dr. Noyori, for sharing your impressive knowledge and experience with us and presenting concrete examples of how scientific innovation is such a significant part of our lives and how, therefore, we must continue to strive towards not only greater but also greener scientific progresses through international collaboration. The distinguished representatives of the host universities would like to take this opportunity to present our honorary guest, Professor Dr. Ryoji Noyori, with tokens of appreciation. May I first invite Professor Dr. Pirom Kamonratanakun to the stage to present a token of appreciation on behalf of Chulalongkorn University.
Should I stay? Should I stay a while?
Now, may I invite Associate Professor Dr. Siri Chaiseri to the stage to present a token on behalf of Kasetsat University. Next, may I invite Dr. Michinari Hamaguchi to the stage to present a token on behalf of Nagoya University. Now, to conclude the ceremony, may I invite all the graduate students in the program onto the stage for a group photo with our distinguished guests and organizers.
Students.
อ๋ออีเวนต์เอาค่ะ
มันยุ่งแย่ไปหมดเลย
Now, if you could please take a picture, a group photo with all the graduate students. So please remain on the stage. Oh, just the AC21. Yes, please.
นั่งข้างล่างแล้วถ่ายจากข้างบนข้างล่างเลย
So this concludes the AC21 International Graduate Summer School opening ceremony. Thank you very much to Professor Dr. Noyori, our distinguished speaker, other honorary guests, organizers, co-hosts, and supporters. Students will reconvene at Kasetsat Start University from tomorrow until June 4th. Thank you very much and have a great evening. สวัสดีค่ะ Here you go.